Hello everyone, I'm Qinghe. I'm a PhD student at Process Intelligence Research Group at TU Delft. Today I'm really happy to introduce our research, process design through deep reinforcement learning and graph neural networks. First, I want to talk about motivation, the challenges for process design. Currently, the transition towards sustainable and secure future demands new processes. This is not only about coming up with completely new one, but also how can we improve and optimize existing processes. So what are the current process design methods? In industrial standard, process design is try and error based on experience. So the engineer utilize the process simulator, try to add unit operation one by one, and do local optimization of operating point. More advanced methods, it involves superstructure-based optimization. Basically, all the possible process alternatives are modeled and then solved by mixed integer nonlinear programming. However, this method has certain limitations. First, it usually takes quite a long time to develop, and since you need to predefine the superstructure, the final process is limited to the predefined structure or superstructure. So can we do better? Can we create a new tool to do quick decision making for engineers? Machine learning may offer new possibilities. It has shown to outperform humans on many tasks, such as image classification or speech recognition. So can we leverage machine learning in process design? Specifically, I want to focus on reinforcement learning, which is a subcategory of machine learning. Reinforcement learning has been utilized in many domains, such as board game Go. DeepMind invented a reinforcement agent that showed the superhuman performance in Asian Chinese board game Go. Some game companies such as Ubisoft also utilize reinforcement learning in some computer games. In chemical engineering domain, reinforcement learning also has been utilized into many tasks. For example, molecular design and process control. If you take a close look, molecular design and process design has certain similarity, especially in terms of structure. Molecules consist of atoms connected by bonds. Similarly, flowsheet consists of unit operation linked by streams. So can we use reinforcement learning in process design? To answer this question, we first need to know what is reinforcement learning. Reinforcement learning generally contains two major components, agent and environments. All the learning process and inference process are based on the interaction between these two. The agent first gets the observation of the current state from the environment, and based on the certain policy, the agent take action. After the action has been taken, environment updated into a new state, and the environment will give certain feedback based on the reward function to the agent to evaluate whether the action is good or bad. In the context of reinforcement learning in process design, again, we also have two components, agent and environment. The agent here you could consider as an artificial chemical engineer, and the environment is a process simulator. First, the agent gets the current flowsheet from the environment, and based on certain policies, the agent takes several actions. For example, the agent could select an open stream, add one unit operation, and then select corresponding design or operation variables. Then the new flowsheet is resimulated in the process simulator, and the environment will give the agent feedback based on the reward function. This is only one step. We need to repeat the whole process again until the flowsheet is completed. as we caught one episode end. As you can see, since the framework is quite complicated, next I will introduce four major components. The first is information representation, which is essentially how can we represent our flowsheet in a machine-readable way. The second is agent architecture. How can we design an agent? The third is action space, which is what kind of action the agent can take. Finally, are the reward and environment. First, let's have a look information representation. Information representation is quite important for reinforcement learning in process design because a flowsheet image here is quite understandable for engineers, but for machine, we need to represent it in a machine-readable way so that our reinforcement learning agent can learn from it. Here we utilize flowsheet graph. Specifically, we represent the unit operation as nodes and the stream as edges. To differentiate different node and edge, we give each node and edge a corresponding feature vector. Within the feature vector for node, we could include the unit type, the temperature, and for edges, we could include corresponding temperature and pressure. Now we have a machine-readable flowsheet graph. We can move on to the agent architecture part. Here we first utilize graph neural network to process our flowsheet graph. The key mechanism inside the graph neural network is called message passing. We take one node as example as colored in red. First, all the node and edge feature from the neighbors are aggregated into a single message vector. Then we can combine this message vector with our original central node feature vector to get a updated hidden state for the node. Importantly, this process is operating on each node within one layer, and the graph neural network contains multiple layers. In the end, each node could potentially get information from the far neighbors. Once the message passing phase is finished, we use pooling function to aggregate all the updated node feature into a single vector so-called flowsheet fingerprint. Once we have the flowsheet fingerprint, we can build our actor-critic network. First, we could have additional actor network to output the actions. Then to evaluate the action agent taken, we have additional critic network to produce value. Importantly, process design is a quite complicated task, so there are many decisions we need to make, which means there are many actions we need to design for this architecture. So how can we design our action space? Here we utilize hierarchical hybrid action space. Hierarchical action means we could have some internal structure within the action space, and hybrid means we could include discrete and continuous action. For example, the agent can select an open stream, which is a discrete action, and then the agent can select unit operation, which is again discrete. Finally, the agent can select continuous action, which is selecting a corresponding design and operation variable. Then here is our overall actor-critic agent architecture, which includes three major parts: graph encoder, critic networks, and actor networks. Then I will talk about the environment and the reward. For the environment, we could use multi-fidelity simulator. For example, for shortcut, we could directly utilize Python-based simulator. Additionally, we could also build an interface to interact with rigorous simulator, for example, D.Sim, Aspen Plus, and Coco. For reward, we also have two types, intermediate reward and final reward. Intermediate reward is response for giving quick feedback to the agent when the flowsheet is not completed. For example, the flowsheet is converged when adding a new column. We will give a positive scalar value to encourage the agent. Otherwise, we will give a negative scalar value. For the final reward, we could utilize purity, net cash flow, utility cost, and we could also incorporate multi-objective function. Next, we utilize a case study to showcase our model. Here, we use a simple reaction, assuming ideal mixing behavior and say is our desired product. For the fit initialization, we use 100 mole per second, 300 Kelvin, and equal molar of A and B. Additionally, we utilize open source process simulator DWSim as environment, and we include 4 different unit operations and a corresponding design variable. Finally, we utilize net cash flow as reward function. Here are the result. There are in total 3 parallel runs. Each run contains 10,000 episodes, and each episode generates a complete flowsheet. And 10,000 training episodes needs kind of 3 days. On the left side hand, this is our learning curve from the agent. In the beginning, we can see the score are negative, because the flowsheet are not economically viable. We can see one example flowsheet, the agent only add 1 unit operation heat exchanger and then close the flowsheet. With increasing episodes, the agent start to learn from the previous experience. So we can say at 250 episodes, the score is already positive now. And if you look at the flowsheet, it already has some kind of structure, reaction, separation, but it still contains many redundant heat exchanger, for example. Finally, when the score converts at 6,000 episodes, the flowsheet is not only economically viable but structurally reasonable now. The reaction takes place in 2 reactors, and then the mixture is separate in 2 columns. However, there's still one limitation, which is the whole process requires long simulation time. The 10,000 training episode need come 3 days. The question is, could we find a way to accelerate the training process? Here we utilize transfer learning to facilitate the training process. Specifically, we first pre-train the agent with our shortcut environment. Then we transfer the pre-trained agent to fine-tune with DWSim environment. Here you can see the result. The green curve is the learning curve from the agent with transfer learning, and the blue curve is without. We can see the agent with transfer learning has faster feasibility. The agent with transfer learning can generate feasible flowsheet even in the first episode. Also, we observe improved performance. The agent with transfer learning reaches even higher convergence score. Also, efficiency boost. Using score of 60 as reference, the agents with transfer learning decrease by 40% training episode. So the conclusion is we propose a reinforcement learning algorithm that represents flowsheets as graph, use graph neural network to learn, and can synthesize new processes. So reinforcement learning provides new possibility for process design. Thank you very much for your attention.